steel design, it is not too often that you get the chance to decide how you want to approach a problem. Normally it's a very straightforward procedure with a very specific way to do it, and there is only one equation that will really get you where you need to be. However, in the case of shear lag, we have multiple cases that could be relevant to our problem. So for this problem, we're going to take a look at an L 4x4 1/2 inch angle with 3/4 inch bolts and A36 steel, spaced exactly like this. And with that, we're going to find the nominal rupture strength using two different cases of U, which is our shear lag factor. One, which we have to calculate using 1 minus x bar over L, and case 8, which gives us a set factor for U. Without further ado, we can get right into it. Pn, which is the nominal tensile strength, is going to be equal to FU AE for rupture. So what this effectively means is our ultimate stress, which by the way comes from the grade of steel that we have, is going to be multiplied by AE, which is right here. But AE can be broken down further into the nominal area times the shear lag factor. And the shear lag factor is what's going to control. Well, I shouldn't say that. The shear lag factor is what's going to have an impact on this net area. So we can start by finding our net area for this problem. It's going to be the same no matter what our shear lag factor is. So our net area is going to be the gross area minus the width of the bolt hole times the thickness of the material that we're dealing with. We can go into table 1-7 to find what our gross area will be for this problem. Since we have an L 4x4 1/2, we can go to table 1-7 because that is our dimensional properties table. A 4x4 1/2 has a gross area of 3.75 inches. Now the width of our bolt hole, we're told that we have 3/4 inch bolts, is going to be 3/4 plus 1/16 for roughness plus 1/16 for bolt spacing, which would give us 3/4 plus 1/8, and that is 7/8. And we have a 4x4 1/2 inch angle, so we can multiply this right here by half. Now that we have those worked out, we can simply plug this in, and it will mostly be a function of figuring out our shear lag from here. So 3.75 minus 0.875, which is 7/8, times 0.5 is 3.3125. Now, we can come back here and say Pn is equal to FU ANU, and the only thing that we don't have is U. So according to this, we need to first, for problem 1, use case 2, and U is equal to 1 minus x bar over L. Now L is going to be the length of this connection here. So L is going to equal 6 inches. And x bar, also from table 1-7. For a 4x4 1/2, we have an x bar value of 1.18. And now we have what we need. 1 minus 1.18 divided by 6, and both x bar and L are going to be in inches, so that checks out. And what we have there is exactly, well, not exactly, 0.083. 0.803. So, according to case 1, our nominal strength is 58 times 3.3125 times 0.803. And we can go in, plug this all in real quick, and our nominal strength is 154.28 kips. Okay, now part B, we're going to do the exact same thing, except our shear lag factor is already determined for us. So FU is going to be 58. We can say AN will be the exact same thing. That will be 3.3125. And I lost the page that I was on in the manual for this, so bear with me for a second. 3.3125. And case 8, with 3 fasteners per line in the direction of loading. With less than 3 fasteners, you have to use case 2, but that's not what we have here. U is equal to 0.60. So, with that being said, one of these, by code, both of these are acceptable answers, but we obviously know that case 8 is going to produce a more conservative answer. That is saying 115.275. So which one of these is correct? Well, technically speaking, by code, both of them are correct answers, right? They are both valid ways of calculating this. If you wanted to be conservative, you would go with this option. However, the technically more accurate answer will always be using case 2. It doesn't generalize, it gives you the exact formula, and it will tell you the answer that is more precise. So if you want a more precise answer, this is the way to go. 0.6 is highly conservative. So you can see how this would change if, say, we had, oh, I don't know. Well, we can't add more fasteners because then it goes to the second part of case, or the first part of case 8, where U is equal to 0.80. But the things that can change are X bar and L. And the way your connection is spaced out will have an impact on the shear lag of this connection. So hope you found this helpful. This is just a good review of how different shear lag factors can be calculated and what is the more precise way of doing them.